Hey there, I'm Teacher Jess and welcome back to Jira Cafe. I hope you're doing well, that you've had a good day so far. Okay, so what I was thinking about doing this time is I wanted to take all of the concepts of atmospheric science that we've learned and put together the foundations so that we understand global air circulation. So that's what I want us to take a look at. I want to understand how the the air moves through the atmosphere across the globe, how the wind is deflected, especially in the different hemispheres. I want us to try and understand the way the wind blows and where we have the high pressure, the low pressure. Hopefully, it will all then make sense in context with the other things that we've looked at. So let me get my screen up. Okay, so I wanted to start by showing you this diagram. This diagram is basically a summary of everything that I want to go through today. So this is an overview of how atmospheric circulation looks. We've got a whole bunch of cells over here, we have wind over here, we have high, low pressure systems, we have all wind blowing in every direction and a big red line. So what I'm going to do is I want to go through each section bit by bit, and then hopefully by the end of it, when we get back to this diagram again, this will make a lot more sense. Okay, let me start on the first slide. Okay, global air circulation. So an overview of how the air moves across the globe. The most important basic thing we need to remember is that warm air rises and cold air sinks. So where warm air is less dense, it will rise up, kind of like a hot air balloon, and cold air is more dense and sinks down. Then if you're looking at it from side view, your sinking air will usually be will be associated with diverging wind. So where the air sinks down and presses onto the ground, it will move apart. It will separate. That is diverging. You may also remember that where the air is sinking, we have a high pressure. So where it's sinking down, it pushes onto the ground and we have a high pressure. And then that air will be pushed away from there. Then on the other side, where we have air rising up, that air is lifted off the ground, so it's not pushing that hard, and it's almost pulling the other air up with it. So we have air that comes together and it's converging. So hopefully this makes sense. That's just the basics. The hot air rises, cold air sinks. When it rises, the air converges towards the rising part. When it sinks, the air pushes away from the sinking air. So we're going to start by first understanding the unicellular circulation model. Then I will break it up into the tricellular model. So the way that we can understand the unicellular model is, actually, I think this diagram is a bit nicer. We know that it is hot by the equator and it is cold by the poles. That makes sense. And where we have hot air, that hot air rises. So you can see it rising away over there. So it rises up and then it diverges into different directions. By the poles where it's cold, that air will be dense and will be sinking down. So we have a circulation system. It is a convection flow, a convection cell. So we've got the warm air rising, it moves towards the poles. When it gets to the poles, it gets cold, it sinks, and then it moves back towards the equator. So this we can kind of see on null school. Bring up null school. Okay, so just pointing out that it's warm over here by the equator. Okay, so it's generally warmer here. And then towards the cold. We'll come back to this. So this is just another diagram of the same circulation model. So we have the warm air by the equator rising. It diverges towards the poles. By the poles, it is cold and it sinks and flows back towards the equator. Okay, but this isn't how the whole circulation actually looks. This is an oversimplified version of it. In reality, there are 3 convection cells. So we refer to it as the tricellular model. So you can see we have 3 sections. Okay, when we say 3, it means like 3 in each hemisphere. 3 up here and 3 here. Okay, so we've got 3 circulation cells up here in the northern hemisphere and 3 in the southern. What I want us to try to do is get this onto a diagram that we can understand. Now, sometimes this whiteboard setup works, other times it glitches out, but we'll figure it out as we go along. Okay, so first thing we need to highlight where the cold area, the warm area is. So I'm going to use the highlighter over here. Let's go with the pink to show that it's warm. Okay, so that's supposed to be the warm area. And then let's grab the marker. I'm keeping it in red because it's supposed to be the warm air rising and moving away from the equator. So it's moving towards the poles. Okay, then it diverges, and because it's colder higher in the atmosphere and it's further away from its heat source, it will start to cool and sink back down. Diverging. It starts to cool, so I'm going to change the color to blue. And then when it sinks, it will diverge again and move back into either direction. I think we need another arrow. That kind of shows it. So it's sinking again and diverges. So right here, I'm just going to add the name. So this is our first cell, and this is the Hadley cell. So hopefully that first little part makes sense. We have warm air rising at the equator. It diverges towards the poles. As it cools, it sinks back to the ground. And then when it gets to the ground, it diverges again. I'm going to do the middle one just yet, because the middle one, so the second one, is a result of the 2 outside ones. So there's a cell towards the equator, that's the Hadley cell, and then there's a cell towards the poles, that's the polar cell. Then the one in between is a result of the other 2 moving. So let's first draw in the polar cell, and then we can connect the dots with the third one. So because the poles are cold, we have air that is sinking and it's dense. Sinking. Okay, because it's sinking, it diverges when it gets to the ground. Okay, in my mind, that arrow is a lot better. That's my story and I'm sticking to it. The polar cell over here, so it sinks, diverges, and we have another convection cell. There, add our label. Great. That's 2 of the 3. Now, the third one is formed as a result of these 2 moving. And here is rising. That movement, let's just connect the dot a different color. Make it purple. Raise that one. Okay, so we see we have the sinking air over there, the rising air over here, and the completed system creates the feral cell. There we have our 3 cells. Hadley cell is driven by the heating at the equator, polar cell is driven by the cold air at the poles, and the feral cell is driven by the movement of the other 2 cells. I realize I didn't highlight the poles to be cold. Do that. There we go. It's cold, just in case you weren't aware. So a neater version of this diagram right here. Right, this is the side view of the same diagram. So we have the equator that is warm. We have the air rising. We have the sinking when it starts to cool. 1 cell over there. The polar cell, we have the cold air sinking. So that creates the second circulation. And then the feral cell comes from the movement between these 2. The feral cell is also driven by the cold front, or the polar front that forms over here. But that is more for the section of mid-latitude cyclones. It's also worth noting that because we have a lot of warm air rising over here by the equator, we get a lot of thunderstorms. So we get cumulonimbus clouds that brings thunderstorms and heavy rain. The next thing I want to point out is where these major changes of air direction happen. So the equator we know is 0 degrees latitude. Put that in. And this is, there we go, 0 degrees. So that's supposed to be the latitude. Not very clear, but it's fine. Okay, then the next thing to note is where the air is sinking. So you can see from the Hadley and the feral cell, it's sinking around here by the 30 degrees latitude. 30 degrees, that is both north and south. At the moment, I'm just drawing the southern hemisphere. "30 degrees south." Hello, welcome back. This is why I'm typing the labels. My handwriting on a little trackpad is terrible. Okay, great. So we have the sinking air at 30 degrees south. Then we have the next section of rising air at around 60 degrees latitude. So 60 degrees north and 60 degrees south. Oh, I realized I completely missed the mark over there. Okay, so far that looks okay. And then purple for the feral cell. that's a little bit better. Now we have the rising air at about 60 degrees latitude, 60 degrees south. And then finally, the last one that we need to include is the poles. The poles at 90 degrees south. The reason why I wanted to highlight these latitudes is because a lot happens at these latitudes. 27 degrees north and south, and the equator, there's a lot of tropical cyclones that occur over here, a lot of storms, like big thunderstorms. That is referred to as the tropical area. The section over here by the poles we know is the polar area, and the section in between, which is mostly the feral cell, that is also referred to as the mid-latitudes. So there we would find our mid-latitude cyclones. So usually around here. So let's take another look at this diagram and let's see if we've covered it all. So we have the Hadley cell there. We have the warm air rising from the equator, moving towards the poles. It sinks as it cools. It will typically sink at the 30 degrees latitude, so 30 degrees north and 30 degrees south. And then it moves back towards the equator, or some of it moves back to the equator, the rest diverges towards the poles. The polar area, we have cold air, it's dense and it sinks, and that creates another cycle over there. And the movement of this cycle and this cycle drives the feral cell. Hope this makes sense so far. Another important thing to know is the intertropical convergence zone. So I always tell my students that they can abbreviate it to the ITCZ as long as they're able to identify the full name first. So in a lot of diagrams, you would see it as the ITCZ. What the intertropical convergence zone is, usually around this red space. You can see that the Hadley cell, the air is moving back towards the equator. Let's draw in a few more arrows. I'm just going to draw the cell in for the northern hemisphere as well. There we go. I think that's okay. And, oh, the poles. Great. Happy so far. Okay, good. We're going to need all of these cells in a moment. I'm going to explain where the global pressure belts are, and then that's when these tricellular cells will make sense. And last but not least, our polar cell rises up when it meets the feral cell. Okay, I think that's not too bad. It's a good basic. So what I wanted to show you over here with the orange arrows is you can see the Hadley cell, the wind blows towards the equator. So the air will rise and it almost pulls the air in from either direction. So the wind blows towards the equator during or 4 times of the year from the north and the south. This area where the two where the two winds meet, where they converge. That is the intertropical convergence zone. There, where that orange line is, that is the ITCZ. And it does move. It's not always over the equator. It does move depending on the seasons. If it is summer in the northern hemisphere, then the sun's focus, the most concentrated areas of sunlight, obviously the hottest areas, will be shifted towards the north. And because that focus, that concentration of the heat is shifting towards the north, the whole circulation system will also shift north. So the ITCZ will be shifting north. There we go, the intertropical convergence zone. I'm hoping this is making sense so far. I'm trying to go through it slowly and clearly. Oh, this diagram is so blurry. It's fine. We're going to rewrite most of this on our diagram as well. So what I want you to notice is where the air is rising and sinking. Where the air rises, it's lifting the air off of the ground, so we have low pressure. Where the air is sinking, it's pushing onto the ground, so you have high pressure. That is where we get our global pressure belts. So I'm going to now draw in those pressure cells across the globe, and then we'll be able to understand how wind is driven from that. We might have to erase the ITCZ. I'll see. Okay, I think we should probably color code it. What color should we make the high pressure systems? High pressure, let's make that orange because it's usually associated with dry areas. High pressure cells are dry. And then we'll do the low pressure cells with the green color because we tend to have a lot of or a more rainfall. Let's start by the equator. So we start with the low pressure. It is warm, so air is rising, therefore low pressure system. And then everywhere where we have the arrows pointing down towards the ground, so the air is sinking, we're going to put in high pressure cells. We have our line of high pressure cells. So the low pressure cells over the equator, those are your tropical low pressure. I need to actually just find the diagram. Wait, where's the names? Let me just find a diagram with all the names. So the global pressure belts. Okay, yeah, that's no better. So I'll just kind of read it to you. Over here we have the equatorial lows and then the subtropical highs. So subtropical means it's just outside of the tropics. Add that label into our diagram. We have that in. So the equatorial lows and the subtropical highs. Now we have another band of lows. If you look at the 60-degree latitude, you'll see again right here, we have air rising. If we have air rising, it's a low pressure system. The name of that low pressure system that I'm going to draw in now is our subpolar low pressure. Okay, so there is our next belt of low pressure systems, the subpolar low. Only one left. The last one is towards the poles. Because the poles are such cold air, the cold air sinks. The sinking puts pressure onto the earth, and that's why we have a high pressure cell at the poles. And that is our polar high. Okay, we have covered all the major pressure belts. Equatorial low, subtropical high, subpolar low, and polar high. So when you look at synoptic weather maps, you'll probably see high and low pressure cells across the map, and you'll see that they align. Maybe or hopefully you'll remember that the high pressure cells are also referred to as anticyclones, and the low pressure cells are cyclones or cyclonic. The next important thing for me to explain is what drives wind. Wind will blow from a place of high pressure to low pressure. So where we have all of these high pressure cells, the wind will be blowing away from it. And where we have the low pressure cell, the wind is blowing towards it. So I'm going to go back to our sketch, and I want to point out the orange arrows that we had in here earlier on. And you can see how it's blowing from the high towards the low. And it goes in the opposite direction as well. Well, I mean, towards the south as well. From the subtropical high towards the subpolar low. And then towards the pole, we have a high pressure over there, so it blows away from the high pressure towards the subtropical, subpolar lows. And that's what we're seeing over there with the polar cell, how it's moving away from the high pressure by the poles, and it's moving towards the feral cell. That is the direction of movement. Hopefully that is making sense so far. Because what I'm drawing on here, the way that those arrows are moving, is not the complete story. They do not blow in a straight line from a high to a low. So what I've been explaining and what I drew on the diagram is the same as this concept over here. So we have a high pressure and we have a low pressure. I drew the arrow as going from the high towards the low. According to the pressure gradient force or the pressure gradient, this is the way the wind wants to move. But it is deflected. Because the Earth is spinning, all of the wind is deflected slightly. We refer to that as the Coriolis effect. So as the Earth turns, Coriolis force is moving the wind into a different direction. And which way it's moving depends on what hemisphere it's in. So in the northern hemisphere, it will move towards the right. In the southern hemisphere, it will move towards the left. And you'll notice that I'm not specifically saying east, west, north, south is the direction it moves in, because it's all from the perspective of the wind, the perspective that it's moving from. So if it's in, get back to my diagram. If this is in the southern hemisphere, and we're saying that the wind starts here, blows towards the low, it will be deflected to the left. So the wind would actually move that way. Now let's say it's the low is the low's to the east of it over there. It will still, with the pressure gradient force, it will want to go towards the low, but with Coriolis force, it will still be deflected towards the left. Now the left is, if it's facing the low pressure, now it's moving left. Yeah, I'm going to add in 2 more low pressure cells and we're going to complete the cycle. Okay, so the black arrow is the pressure gradient force, and now the wind Coriolis force will be deflecting it left. So the purple arrow, there we go, deflecting it to the left. And you see it's always left from the direction it's moving in. So imagine yourself standing at the high pressure, looking at the low pressure, then you go left. Now I want you to notice the direction of the purple lines. You see that they're starting to circle. Okay, hopefully I've put in enough left pointing arrows for it to make sense. I'm going to take this one out. Yeah. So you'll notice that around the high pressure, when it's blowing away from the high pressure and deflecting towards the left, it's taking on a anti-clockwise movement. That is why anticyclonic is anti-clockwise in the southern hemisphere. In the northern hemisphere, let's do the exact opposite. Okay, so in the northern hemisphere, everything would deflect to the right. So now as I draw in the arrows, I'm going to draw them pointing towards the right. Okay, so as it deflects towards the right, around the high pressure cell, you see it moves clockwise. That's why in northern hemisphere, anticyclonic is clockwise. And in the southern hemisphere, anticyclonic is anti-clockwise. It all comes down to Coriolis force. So northern hemisphere, Coriolis force is towards the right. Southern hemisphere, Coriolis force is towards the left. And that's where you see this. So you see the high pressure belt over here. You see the winds trying to move towards the low pressure belt, and then it is deflected towards the left. Then the high pressure cells in the northern hemisphere is trying to blow towards the low pressure at the equator, and now it's deflected to its right. Remember, you have to imagine yourself standing over there, looking towards that direction, and then move to the right. That is how the wind blows. I'm really hoping this is making sense. So the last thing I want to do is erase the arrows that I've already put in here and draw in what the correct wind direction would be in the southern hemisphere. It's a lot easier to work with an actual whiteboard, but you can't save the board. Okay, so we draw a few in purple. We're going to start by the equator. So, by the subtropical high. So from the subtropical high towards the equatorial lows, it will deflect to the left. And then when it blows towards the subpolar low, again, it is deflecting to the left. And that would be its left, not our left. Okay, and the last one we need is the polar high. So blowing away from the polar high towards the subpolar low, towards the left. So I'm just going to put in a few from the northern hemisphere. So if it's blowing from the subtropical highs, so that's the 30 degrees north, towards the equatorial low, now it's deflecting to the right. And the reason why I wanted to put those in is because I want you to see how they kind of align with the wind that's coming from the southern hemisphere. So they are converging and they're blowing into the same direction. These winds are our easterlies. You can see that they're blowing from the east over here, and they're converging and blowing towards the west. So these are our tropical easterlies. Okay, so you have northeasterly trades, southeasterly trades. You can refer to them as the easterly winds or the trade winds. I'm fine with either of my class. And then the ones blowing towards the south from the high over here, those are our westerlies. Go, there's the westerlies. And the ones blowing away from the high pressure at the poles, those are polar easterlies. Okay, I think I've covered all the winds. So let's check if I'm missing anything. We have the trade winds blowing towards the west from the east. We have the westerlies. There's only one band of westerlies. So we have your tropical easterlies or your trade winds, and you have your polar easterlies, but you only have one band of westerlies. That's why they're just called westerlies. And then, of course, polar easterlies. Okay, reminder, Coriolis force towards the left in the southern hemisphere, towards the right in the northern hemisphere. As soon as you've memorized that, all of this becomes a lot easier. So there's just another version of the same diagram. This is basically what I was drawing on that other diagram. We have the cells, we have the air rising, it sinks, it creates a high pressure cell. This is our Hadley cell, the Hadley circulation. Cold air sinking, creating the polar cell, and then the drive between the two is the Ferrel cell. Okay, so there's our three cells. Here we have the low pressure, equatorial low, also referred to as the doldrums. Here we have the subtropical highs. Here we have the subpolar lows, and of course the high pressure poles. Okay, then you always have the wind blowing away from the high pressure towards the low pressure and deflecting towards the left in the southern hemisphere, right in the northern hemisphere. Oh, that's the last one. Sorry, I thought I added one more. Okay, so hopefully now looking at this diagram, it makes more sense. We have the tricellular model, Hadley, Ferrel, and polar. We have the pressure belts, that is low, high, low, high. We have the wind blowing from the high to the low, deflecting left in the southern hemisphere, right in the northern hemisphere. And that's where we get our easterly trade winds, our westerly winds, and our easterly polar winds. Okay, I really hope that this has been helpful. I wonder if we can see any of this on Null School. It'll play along. I'm going to close FigJam because I think it slows things down. Hey, let's check out Null School. There it is. I think it's moving a bit. I think it's working a little bit better. Okay, so that's a little bit more neutral. That's in, I think, did I set it to March? I think I set it to March. It doesn't matter. We can still see. Okay, so you can see that the winds over the equator is blowing from the east to the west. You can see that the wind over here, there's also where the jet streams are, that's the very strong westerly winds. And unfortunately, the winds around the equator don't seem to be that strong in the simulation. But I am hoping that this has made sense. Hopefully answered a few questions. Any last questions before I wrap up? Okay. Well then, thank you for joining. I hope that this has answered a few questions. Maybe you learned something interesting. Hopefully it's helped. This is the foundation for a lot of sections of atmospheric science. I kind of skimmed through these basic concepts in other videos, and I thought it was necessary to have one video that looked at these important forces. So hopefully we understand global circulation a little bit better and have an idea of how Coriolis force works. Otherwise, I hope you have a great day and that I'll see you next week. Thank you for joining. Cheers. Bye.